Hello, everyone. So just want to make sure you can see the slide page. Okay. Can you see the
sir.
slide page?
Yes, sir.
Yes, we can.
Thank you. All right. So because we are more than halfway of the semester, so we should begin to start to prepare for teaming up for the final project. Okay. I think next week we will release the final project. We are still sorting out the data. Okay. So when the data is ready, we'll provide maybe a couple of projects for you to choose. Right. So the final project will be given, but if you have your own idea of doing a final project, just let me know, okay? So the purpose of final project is to make sure you will be able to do big projects, right? So using tools that you're not that familiar with, right? So if you just call some libraries that is already in scikit-learn on some public data set, that may usually not qualify, okay? So we want the final project to be slightly more larger, okay? Slightly larger than a regular mini project. Okay. Another thing is that we have released the first written assignment. It covers 2 lectures. Okay, so the lecture for today, as well as the lecture for the previous one. Okay, the previous one is quite daunting, right? So because we have maybe 70 some slides. Okay, mainly on optimization, how to find the parameters. Okay. And that lecture is about generative models. And today we will look at discriminative models, right? So for both are for classification and regression. Okay, supervised learning. Let me see. So I think one student mentioned that he cannot find the written assignment. Let me try to see. So on this page, let me send an announcement. Okay, so that everyone will get a notification. Yeah, so for the first written assignment, if you go to assignment 1, let me see whether it's not it's not published yet. Okay, let me publish it. Okay. Yeah, sorry for this. So we will count from midnight today till next Wednesday. Okay. If you need extension, you can let us know. We will probably not have more penalty till the end of that week, but we will have to release the next programming assignment. Okay, the mini program project 3, which are actually dependent on this assignment. Okay, so written assignment 1's conclusion will be used in the next programming project. Okay, so we encourage you to finish by November the 4th. Okay, if you cannot, you need to request for extension, but no later than that week. Okay, but we will release the next assignment anyway. Okay, so assuming you already finished it. Okay, and so yeah, so this is a written assignment. Another thing is about teaming up for the final project. Okay, so the TAs will still do their office hours as before. Okay, and so the difference is that the TAs will set up some breakout rooms, like chat rooms, which basically the TA will not chat with you guys. You can find a bunch of empty rooms where you can chat with each other, and you can join and have the private conversation, right? So what I'm thinking that usually if you go to the main room, so you can chat with each other, hey, who want to team up, right? So and then if you find a couple of guys after some chat, really like to form a team, then you can find an empty room and then go there and chat privately, okay? And to confirm the team for them. And we will enable the teaming. So it will be a self-registration on Canvas. Okay, we will enable that next week, right? So let's start to forming teams. Okay, and for both TA office hours, they will enable the breakout rooms. Okay, and the TA will be doing Q&A in the first breakout room. So you will find another breakout room. okay? Because the TA may want to answer the questions of a student one at a time, right? So only one student will be, in the breakout room number 1 with a TA at a time. And then the TA, when he finishes, he will let you guys know, okay, by sending a message. And the next person can just join, right? So, and in the main room, basically you can chat freely. The TA is not even there, right? So this is the setting to help you guys forming teams. Okay, have somewhere that you can chat, right? So this is the arrangement. Any questions before we move on?
Yeah, yes, sir. So the first student assignment is labeled as a homework1.pdf.
Yeah, homework1.pdf. Okay, so we have 5 questions, and we will go through briefly what you need to pay particular attention at the end of this lecture. Okay. Right, so these are the five questions. Okay. Okay, and also the slides for today is also released. Okay, so linear discrimination. Okay, linear discrimination. Okay, we also cover the other topic of logistic regression that are closely related. Right. So yeah, let's begin. Okay, so here we are talking about linear discrimination. Okay, so in machine learning, discrimination is equivalent to binary classification. Okay, keep that in mind. Right, so let me enable the pen. Let me see. It's detecting the pen. Okay, it's working. I cannot see the. It doesn't seem to work well with it's the one. Somehow I cannot find my mouse, so I think I cannot use Zoom and play together. The mouse pointer will be missing. So let me use this. Okay, that's it. Okay, I think that's a Zoom button. So discrimination is equal to binary classification. Okay. Let me try to binary classification. Okay. Right. So one example of where we will call discrimination is, for example, if you there's a model called the GAN, which is the deep learning model that let me see. Yeah, maybe this is good. Right. So you want to create some generator that will generate realistic images. Okay, that may not exist, but when you see it, it makes sense, right, from your pile of data. Okay, in order to do so, basically you should have a binary classifier. We call it discriminator. So you see the discriminator is binary classification, binary classifier. Okay, so it will not be able to detect whether this generated image is real or fake, right? Because it's fake, but if it's really realistic, it will look like real. Okay, so you can give a real image, it will rank as real. If you give a fake image, also we hope the discriminator will rank as real. Then it means the generator is good, right? So in this example, again, we'll have 2 models. One is called a generator, one is called a discriminator. Okay, this is a generative model, this is a classifier. Okay, but this classifier is binary, right? True or false. Right. So discriminator is just a classification, but it's a binary. Okay, keep that in mind.
Professor, here the discriminator takes the input of both generator and the real image, right? And then decides whether it's a real image or not.
No. So basically, when training, it's a 1 entry at a time. So usually if you have in deep learning, actually, it's a mini batch. Right. In our graduate case, it's a 1 row at a time, right? So this is maybe a 1 row, this will be another row, okay? Right, so this is 1 at a time, maybe go to real or fake. This is another time, okay? It's just putting them together for illustration in 1 image, okay? Do I answer your question?
Yes.
Okay.
Thank you.
You're welcome. Yeah, but this is irrelevant here, okay? You just keep in mind discrimination is binary classification, okay? That's all we need to know. So this is linear binary classification, right? So basically you have a linear hyperplane. On one side it's positive, and the other side is negative. Okay, so this is what we mean. Okay, let's take a look at the introduction. Right. So in the previous lecture, we looked at a so-called likelihood-based classification, right? Because we go to the Publix model, right? And so basically what we have here, let me try to avoid the pen in Zoom. Okay, we use the pen in slides, okay? Likelihood-based classification, we assume a generative model, right? Given a class C, how likely to be X. We also call it, the formal name is called a class conditional probability density, right? So this is probability density, small p, not big P. Right? Big P is for discrete variables, okay? And this is class condition on the class, okay? But we just call it generative probability, right? For simplicity. It's actually a density and it's conditioned on the class, okay? And we will define some way of generating data, okay? The generative probability. In our case, we actually define something parametric, right? Like a Gaussian distribution. But you can also define something like a semi-parametric or even non-parametric. Semi-parametric is like a Gaussian mixture model that we will look at later. Okay, so let's continue. So what you do when training the classifier is very simple, right? So if you remember, what we do is right. So we have a table, right, and we have a class attribute, right? Class 1, 2, 3, etc. Okay? And then we also have some regular attribute for prediction. Okay? So they have some values. Okay. So what we do is we estimate the two probabilities, right? So this probability is estimated from the portion of 1, right? So how likely your class is 1, right? So prior is, let's say if you have 10 data entries, 5 is 1, then it's 50%, okay? And the other, let's say it's a Gaussian distribution for the class conditional probability. Then in this case, we will look at all the 5 rows that are belong to class 1, and they use their sample mean and the sample convergence matrix to fit the Gaussian, okay? This will be that Gaussian. And then what we do is we apply Bayes' rule to compute the posterior. Right? So we know that the generative model times the prior equal to the posterior. Okay, of course it's proportional to, right? It's divided by px, but this px is constant. We ignore it. Okay, for different classes it's the same. Let me clear this a little bit. Okay, and finally, so we perform the optimal classification based on what? Based on this probability, right? So this probability basically is posterior, right? When you see X, how likely you belong to class 1, how likely you belong to class 2, how likely you belong to class 3, right? You definitely assign to the most likely class when you see X, okay? So this is equivalent to if you say, hey, we have a discriminant function that is kind of have the same trend as GCI, okay? So we call this discriminant function as GI, okay? GIX is basically saying that we can take log, right? We take log and doesn't take log, it's the same, right? If we find the maximum class C2, maximum P C2, okay? It's also maximum log P C2, right? And so discriminant function GI, why we call it discriminant function, right? So if you remember, we say that it's a binary classification, right? Now we can have a lot of classes, C1, C2, C3, right? So this is still a discriminant function because this is for a particular class, right? So for example, G2 is for class 2 or not class 2, okay? This includes class 1, class 3, class 4, but we don't care. Okay? Either class 2 or not class 2, it's still binary. So this is basically, okay? Any questions? Yeah, if not, let's look at the other one, okay? So previously we talked about likelihood-based classification. Basically, in order to get this discriminant function, which is a posterior probability, right? We need the prior and the general probability, okay? And another way to do that is not go through the probability model at all. Okay, we directly assume the shape of the discriminant function. Okay, we directly assume the shape of GI, right? And then we find this is like the score of a class, right? So we find the class with highest score. Okay, the score of that class CI is the function GI. Okay, and it depends on the input features. Right. By the way, for the whole lecture today, it's about classification. Unlike last time, we have regression, we have classification, we have density estimation. Today, we all do classification, okay? density estimation is basically estimated this density, right? Any questions? Yeah, so discriminant function is a little bit different, right? So assume a model directly, right? So for the discriminant functions, we don't go through the probability model, like the general probability or posterior, okay? So what we do is we just say, hey, GI is of this shape, right? So then we fit those GI function parameters, okay? And then we find X, we compute all G1, G2, G3, find the largest one, right? Let's say G2, then your X belongs to class 2, right? So this is perform optimal classification just based on these discriminant functions. So what's the main difference between the likelihood-based classification and the discriminant-based classification? As a summary, the main difference is that likelihood approach actually is based on the probability densities, right? So this one, okay? How likely you will generate X when you belong to class 1, okay? But discriminant-based approach had no such assumption, okay? It directly assume what's the shape of GI, okay? What's the shape of GI, right? So we bypass all those Bayes rule, etc. There's no Bayes rule, basically. Okay? Any questions? If this is okay, let's continue. Right. So yeah, now that we say that for each class we have a function that is a function of X, right? But different class should have different function parameters, right? So that's why for different class, when you put the same X, they will have different scope. Okay. And yeah, so let me see. So here you can see that, let's say we have 3 classes. Right? Let me call out my pen. We have, let's say, class 1, class 2, class 3. Okay. And for each class, we have a parameter. Parameter 1, parameter 2, parameter 3. Okay. So this is actually the same. If you recall, let's say in our previous example with likelihood-based model, right? Generative models. There we have the Gaussian distribution for class 1, Gaussian distribution for class 2, Gaussian distribution for class 3, right? The parameter will be the mean of the Gaussian and the covariance matrix, okay? But here we directly assume the shape, right? We directly assume that the parameter, let's say this function is linear, okay? Which is actually what we are doing in this lecture, for simplicity. So we do have a bunch of parameters, one for each class, okay? And learning, what is learning, right? So just like scikit-learn, you have a model, you call fit, right? What are we doing when we call fit? Right? We are trying to find those 3 parameters, phi 1, phi 2, phi 3, okay? When we learn that, when we call the predict, right, then we just put X into each of the functions, right? Get 3 G scores, G1, G2, G3, and then find the largest one and return that as a class, okay? So that's if you go to scikit-learn language, right? Fit is learning these files, okay? And predict is just to say, hey, then I put X into those functions, which so far as I already determined, then I find the high score class, okay? And yeah, any questions? If not, let's continue, okay? So discriminant functions, right? So this is not like likelihood-based approach, okay? We don't have density estimation. So density estimation, one useful case is because you are using Bayes rule, right? One of the component is density, right? Probability density, right? Because you have probability times probability, etc. Right? Times general probability, and maybe there's a graphic models, okay? So yeah, let me briefly explain what is the graphic models. We will not go through that, but graphic models is a little bit more complicated. Okay, let's say you have a prior A, okay, and then you know that there's some distribution from A to B, right? So for example, then you have B, you know that it depends on A, okay? And then you have another prior, let's say PC, okay? That is another important factor that is prior, okay? And then maybe you have another thing that is something like this, right? So you have another conditional probability like a D, okay, which is dependent on A and C, okay, right. And finally, so this is basically a table, by the way. So this thing is basically a table, right? So it's a conditional table, right? So you have A and C with different values, right? Then what will be your D's value? Okay, right? So A equal to 5, C equal to 6, D equal to 2. What's the probability? Right? So it's a table, okay, conditional table. Right? Finally, maybe our final Y. Final Y, right? So is a function of B and the D. Okay. Right. So you will have these two arrows formed together. Okay. So this is a directly graphed model. You cannot have any circles. Okay. You cannot have a cycle. Okay. So you cannot go back and another arrow go back. Okay. Otherwise it will not break. Okay. So in this case, how do we derive the joint probability? Right. So I can tell you this is very simple. Just times these 5 probabilities together. Okay. Right. So usually this is by domain knowledge, right? You know that the variable A, variable C, and you know that B is only dependent on A, and you know that D is dependent on A and C, right? And then you have B and D can determine Y, right? So this is how people in graph models publish tons of papers, right? So they have a specific problem. They know, hey, let's say this is weather, right? Influence how many cars on the road, right? Or what's the speed, right? So they know this. And another factor, like, let's say the time, right? So maybe it's peak hours, right? So you can do a density estimation on here. We will learn something later. Let's say you can use a kernel density estimation, right? So there's another non-parametric method, okay? Right? Or you can use a Gaussian mixture model, which is a semi-parametric method. Here you can assume Gaussian, right? So then you can say, hey, I know that using domain knowledge, I know that A and C both determine D, another factor, right? Finally, so basically if you build this model and it really correspond to your application domain, right? So variables really satisfy the requirement, then this model will work pretty good. Well, all you need to do is to maximize the joint probability given the data you see, okay? Given X, right? So all of them will be conditional on X, but we'll ignore them, okay? Because it's on the right-hand side after the conditions. Okay, so we just okay. So when you see X, the joint probability is basically, let's say, P, A, B, C, D, right? Okay. Y is like A, B, C, D. Okay. I think it's not so sensitive. Okay. So why is this the case? You first think about timing these two together, right? So when you type these two together, this becomes PAB. Okay. Let me see whether we have a way to clear it a little bit. No, let's just assume these two are timed together, just give you PAB, okay? PAB, okay? And then if you time C and this term, and then PAB together, okay? Right, so you will see that it's actually PABCD, right? Because, on condition side, it's A and C, and then you time those not on condition side, also C, also A, then they just move to the non-conditional side, right? So this becomes PABCD, okay? And then finally you times Y, okay? So this becomes what? This becomes, because, PABCD has BD already on non-conditional side, right? According to the conditional probability, if you this thing has BD, right? So this will go to the front, okay? So this really becomes the joint probability. Maybe the target variable is Y, okay? So any graph models, if you time them together, it will become a joint probability, conditional X, right? And then you want to maximize the likelihood, right? Using maximal estimation. Okay, this is actually basically a way that people publish maybe tons of papers. Okay, so for each domain, you have different variables. Then you build those probability models, assume reasonable probability distributions, or fit from the data. Okay, using kernel density estimation, and then you can do the derivation. Okay, so in this kind of graphic models, the parameter are those tables. Okay, those tables. Right. So in our case, we are considering a very simple model. Right? You have a prior and arrow to the general probability. Okay, that's what. Yeah. So, any questions? If not, let's continue. Okay. Once you have the probability, then you take derivative. Right? So then you do some mathematics and show the derivative form, and then do the gradient descent, and you publish it. Okay. And so this is discriminant function. Okay. And so as the, let me see. So what's the difference from before, right? So what's the difference from likelihood-based method, right? If you remember what we talked about likelihood-based method, okay? We mentioned that there we will do the general probability estimation from all the rows for class 1 first, right? And then for class 2 first, then for class 3 first, right? For class 1, we'll get phi 1. For class 2, we'll get phi 2. For class 3, we'll get phi 3, okay? But in discriminant-based method, we don't do that, okay? We don't do that one at a time for each class. We estimate them for all classes simultaneously, right? So, and then we find the decision boundary. Right? On one side it's positive, on the other side it's negative, okay? So this is another difference, and you will see that later in this class. And so actually this is easier, right? Estimating the class boundaries is easier than solving, estimating the densities. Okay? Because for densities, you need domain knowledge, right? You know that this variable will impact that variable, and they are following this relationship. Okay, let's say if you have GPS coordinate, you know the noise is maybe Gaussian, right? With that variance. Okay, that's standard deviation. If you model it wrongly, then your model will not be accurate, right? Any questions? Okay, let's continue then. Okay, so yeah, so now let's consider the simplest form of discriminant function. Okay, so here GI is, when you have X, what's the score of X for class I? So this parameter phi I is determined by only two terms, AX plus B. Okay, this is a linear function, right? So this is, because we're considering a bunch of, attributes, right? So each has a weight, basically. Okay, it's an inner product, which is basically this, right? And what's the advantage of using a linear function? Right? So later we will see how to handle the case that the linear function does not work well. Right? A lot of data, it's not linearly separable. Let's say, for example, if you consider our previous example, right? So you have a family car or luxury car, right? So you have the speed and engine. Right? So you know that it's like in the middle, it's family car, right? And on the other side, it's not family car, maybe sports car or Larry Clark cars. Okay, it's not linearly separable. If you separate this side is okay, it's all non-family cars, but this side has family car and a non-family car, right? So not all functions are linearly separable. Not all data can be linearly separable, but we can find a way to address this problem by doing some tricks and still be able to utilize the linear function. Basically, we will change the feature to another space. Okay? We will see that later. So linear function is always important, okay, because we can convert it then later to handle nonlinear cases. Okay. And if you know a little bit of deep learning, right? You know that no matter whether it's dense layer or it's a convolution or it's recurrent net, basically a graph neural network, all the others are basically dense layers, right? So the only difference is the convolution. It's a sliding window. Right? All of them are just the linear matrix multiplication. Okay. So then you add some nonlinearity like activation function. Okay, we lose this kind of thing, right? If you know that. But just want to emphasize the linear is very important. Okay, this is a fundamental module in machine learning. Right? And the benefit of using a linear model here, if you can, it can work well. Why we want to use the linear model, right? Because it's OD time and space complexity, right? So you only store D weight values. Okay, maybe D plus 1. That's not so important, right? In terms of asymptotic complexity, okay? And the time is also linear, right? So D, right? Because you do D times multiplication and D minus 1 times summation, right? And plus this summation is D times summation, okay? And another is understandability, right? So why is this important, right? So for example, if you consider, let me see. Okay, yeah, so let's assume we have 3 parameters, okay? So what we will have is W1 times X1 plus W2 times X2 plus W3 times X3, okay? Plus W4, maybe, W0, okay? So if, let's say, after you call the model fit, right, so it will train those 3 weight matrices, weight parameters, We decide, hey, W3 is almost 0, right? 0.0001. Okay, what does this mean? That means your y, your g, is irrelevant to x, right? So x, whatever value it is, it does not impact the score of this class, right? On the other hand, if your value is very different from g, then it impacts x2, let's say. It impacts y a lot. If this is 100, okay, that means, hey, the larger your x2 is, it's a larger impact on y, right? It's very positively correlated, right? If this W1 is negative 100, right? That means it's still highly correlated. It's just a negatively correlated, right? If you, let's say, you play a lot of computer games, right? So your score is very low, okay? Right, so that's related, okay? There's a correlation, right? So only when it's 0, it means, hey, this is orthogonal to this y, okay? It doesn't matter, right? So this is, you know, the weight itself gives interpretability, okay? And finally, there's accuracy, okay? The model is very accurate if some assumptions are satisfied, okay? And one assumption is the Gaussian density forecast have a shared covariance matrix. If you remember last lecture we talked about, right? So if your covariance matrix is shared, right? So the quadratic term is gone, right? So then it becomes a hyperplane. Otherwise, it will be a curve, right? You still have the quadratic term for this separable planes, okay? Separable surface. Any questions? If not, let's continue, okay? Because we need to finish this slide today, if possible. Okay. Yeah, so as we said, maybe some data, like the car engine, right? So the family car classification problem, this cannot work, right? So how do we handle this case, right? So when a linear model is not flexible enough, it can be generalized to a generalized linear model, okay? By adding, for example, we can add a high order terms. This is one example, right? We call it a product term. Let's think about, let's say we only have 2 inputs, right? So maybe car power and the price, right? So we can define new variables, right? So from these 2, let's say you have 2 columns, right? You create another column, take the first column's value square, right? The second column takes the fourth column takes the second column value square, right? If you are doing in pandas, it's super simple, right? Just the data frame and new column name equal to that old column square, okay? Right. So if you have, say 5, okay? Yeah, again, so we didn't cover a lot of pandas, right? So pandas is for data pre-processing, data cleaning. And then when there's no missing data, you go to second, okay? So for programming side, you need to know these things and you practice yourself, okay? And finally, we also have another projector, right? So we don't go beyond the projector, right? So you have x1, x2, right? So basically these first 2 columns come together. Then we create a new table with 5 attributes, right? Even though, you know, the last 3 can be computed from this first 2, right? But then, if we define a linear function over this, okay, so basically what we are saying is we can define something like W1, Z1, okay, plus W2, Z2, okay, plus W5, Z5, okay. Then this function is very powerful, okay. Let's take a look at a particular example. Just think about a circle, right? So let's say family car is belonging to this circle, okay? And we have radius R, right? So we know this is A, this is B, okay? And we know that this circle can be described, I think from high school mathematics, right? You know that. Let's say this is X, okay? We can use X1, X2, okay? This is X1, X2. Maybe in high school mathematics, we use Y for X2, right? So this is basically, we say that it's X1 minus A squared plus X2 minus B squared, okay? Should be less than or equal to R. If that's the case, it's a family term. Otherwise, it's not family, right? But if you take all these terms, right? So you can see this term is what? This is x1 squared, right? Which is one of the terms, right? So the coefficient is 1. W3 is 1, okay? And this is x2 squared, which is this term's weight, okay? And there's also other terms, maybe, right? So there's a 2ax1, right? So this is this weight. 2ax, it's this weight, okay? And finally, you have the constant. Constant is basically W0, okay? We also have we also have a bias term, just like, okay? And so you can see using this transformation, so add additional columns, right? And we can just scale up the model to be able to separate this kind of data, right? Well, if you just use a linear plan for x1, x2 directly on this two-dimensional space, you can never do it, okay? Any questions?
So I have a question here.
Yeah.
As you said, using circle, the geometry, we are able to segregate the high price and low price cars. But what if we have 3 or 4 or 5 many variables? How to visualize this and solve this problem?
Yeah, I understand what you want to say. So basically, this is what we want to say. So you can create an even cubic, okay? And you can capture more complication, right? So basically, we are saying is this. So this is not linear separable data, right? So if you define some features over the original features, okay, and then apply a linear model over the new features, Z1, Z2, Z5, okay, that will be more powerful, can describe more powerful shapes, where a linear model cannot do. That's all the takeaway. This is a toy example, okay? Usually in the high dimensional space, like 5-dimensional space, we have no way to get intuition, okay? Just like what we talked about for multivariate calculus. You can only go to low dimensional to get intuition, right? And then people will tell you, hey, these people use these solutions on high dimensional real data and they really work, okay? Then you accept this. You know these things are working. I understand that a lot of you want to get intuition. So this is basically, unfortunately, in machine learning, we are going from complex things to simple case to get intuition, right? And then you generalize back to say this is correct, okay?
Well, Professor, I got your understanding, Professor. But
Yeah.
what if here we have 2 variables? Let's say we have 3 variables. Then the number of combinations Z3, Z4, Z5, there'll be multiple, right? Should we go in the same manner or?
Yeah, there are x3 squared, x1, x3, x2, x3. Yeah, there will be more. Okay.
Yeah. Okay. We need to try all those things. I mean, just for understanding. That's what takeaway, right?
Yeah, this is a takeaway. Okay, so later we will see if there's a support vector machine kernel that solves the problem. Okay.
Kernel
you
trick.
have infinite dimensions it can handle. Okay.
Okay.
We will see that
Thank
later.
you, Prof. Thank you.
Okay, so basically you can transform the original space into an infinite number of new dimensions. Okay, the support vector machine can handle this, and infinite dimension is super expensive, but using kernel function, it can bypass the computation overhead.
And Professor, I have one more question here. Does the Z5 creates any multicollinearity problem in any of the discriminating functions?
Can you repeat your question?
Z5 variable, does it create any multicollinearity problem?
Create what problem?
Multicollinearity.
What is multicollinearity?
I mean, dependency between the multiple variables will cause decrease in the accuracy of the prediction, right?
No, you have the weights, right? If you think that term is not good, you just accept that particular W4. Let's say you don't have project term, you set W4 to 0. That's it. Okay? It's a weighted sum. It's okay? Right? If you think the x1, x2 is not important, you set the model will learn it to be 0. It's okay?
Okay, Professor.
Right. So W will be fit according to the data, right? All right. So that's hopefully I answer your question. Okay. Yeah. Once you do this kind of feature transformation, you will be able to capture more complicated shapes, right? We call it nonlinear, right? Nonlinear actually is richer than linear, but it's super complicated, right? It's like a alchemy, right? So you just think, oh, this is a way more complicated case. We can still cope with it. Okay. We need to have this this kind of spirit, right? Kind of go beyond what we understand, but things are working, right? So then we live with it. This is the machine learning. Okay. Unfortunately, machine learning is not 100% accurate, so you need to know whether the accuracy satisfy your application requirement or not. Okay. All machine learning is doing is minimize the error or maximize the likelihood, right? Whether the error is too big for application, right? So that's no guarantee. Okay, so it's just a final parameter, minimize the error. Okay, and so the previous method is already, we can call it a generalized linear model, right? So for generalized linear models, you can actually define your features, right, as a function of x1, x2. Okay, Right? So, and if you want to go to SVM, actually it defines those features for you. Okay, so there are slight difference. Okay, so generalized linear model is called a GLM. Okay, basically doing this. Right? So it defines nonlinear functions in the original input space. Okay, because if you define linear function, let's say you define this 3 to be x1 plus x2, it's useless. Right? So if you w3 x1 plus w3 x2, right? You can merge with the first two terms. Okay, so usually we will define a nonlinear function. Right? It can be any nonlinear function. Right? X squared is a nonlinear function, log x is a nonlinear function. Right? And so in this way, let's see. Okay, so define a linear function in nonlinear transform new space to not increase the number of parameters significantly. Okay, so this is what we want to say, right? So originally we have x1, x2, then we have two parameters, w1, w2, right? And now if we increase it to like 5 dimensions, right? We have w1, w2, w3, w4, w5. Okay, so in this case, the number of parameters is still acceptable. Okay, right. It's not increasing like to 1 million parameters. And here we call, so each new feature, right? So the new feature z, we define the z as a basis function. We call it this basis function, right? So phi ij, okay? We call it the basis function. The reason we have I is because we are considering a particular class Ci, okay, class I, right? Otherwise, you can just ignore the I. Right? Then this is the j's new attribute. It's like a Cj, okay? Z3, right? This is a j's new attribute, which could be x1 squared, okay? And this is the corresponding w3, okay? And then we add them together into a linear model, but that's just for one particular, discriminant function. For class 1, for class 2, you have another I, okay? So that's how you interpret it. For simply, it's a linear combination of the, of the new features, give you a discriminant function, right? So here, as we said, the discriminant function phi ij can be any nonlinear function. But here are some examples. It can even be this. This is basically saying, hey, if it's less than x1, it's 0. Okay, if it's larger than x1, it's 1. Right? So it's an indicator function. Right? So basically, it's something like right. So let's say this is your phi. Right? So this is x. This is c. This is x1. Okay. So less than x1, it's 0. Beyond x1, it's 1. Okay. So this is useful in a lot of cases. For example, if you know that if the score is too low, right? So probably you will not recruit that student, a PhD student, right? So only when it's beyond certain levels, I look at the other feature, right? Whether research is strong enough, right? So whether smart enough, etc. Okay, right? And so then you have different ways to play together. Okay. Right. So yeah, so generalized linear models are related to kernel methods. They are different, by the way. Okay, if you look at the libraries, you will have a GLM model, okay, where you define the features yourself. And the model will learn the parameter, like the C, the N for you, okay? So SVM actually defines those features for you, okay? Defines those phi ij. Right, we will see that later. SVM is not the focus of this lecture, maybe 2 lectures later. And now let's take a look at a geometric view of the linear discriminant functions, okay? So firstly, one thing you need to pay attention, as we said, binary classification is always special. You can eliminate half of the parameters, okay? So here's an example. If you have 2 classes, right? So, and you know that the first discriminant function is w1x plus w1z. The second discriminant function is w2 times x plus w2z, right? And then you see which one gets a high score, right? But you can define a gx that equal to g1 minus g2. If that's the case, this x can be taken out. It's basically w1 minus w2 in the product x, right? So this constant also can be put here. And then these two are new parameters. We can just write them as w0, this as w vector. Okay. So then what we can do is this, right? So if gx is larger than 0, then we will choose class 1. Okay. If g0 is smaller than or equal to 0, we will choose class 2. Why they are equivalent? Okay. So this is because, what does this mean by gx larger than 0, right? So this means gx is larger than 0, right? Which means g1 is larger than g2. So you belong to class 1, okay? Otherwise, you belong to class 2 because this guy is large, right? So basically, it's equivalent, but we don't need a 4 sets of parameters, okay? We can just use 2 parameters for simplicity. They are equivalent. Is this okay? Yeah, I hope this is okay. Right. So next, let's look at the concept of GX, right? So here we eliminated G1, G2. We only consider GX because we are considering binary classification, right? And in binary classification, so what we consider, so here we are only looking at X is a 2-dimensional, right? In general, it will be high dimensional. If it's a high dimensional data, in a high dimensional space, it will be hyperplane, right? In 2-dimensional case, it's just a line separating to subspace, okay? Right, and we know that GX itself is a linear function, right? So this is this, okay? Right. So if we come back here, we can write it something like this, right? So so it's the same thing. Okay, this is basically W transpose X. Okay, they are vectors. Oh, in other words, this is row vector now, right? Because transpose. This is W1, W2 times X1. Okay, this gives the inner product. These two and add a bias. It's okay. If we don't have bias, if W0 is 0, right? So then we will be passing through the origin. Okay. Because if x1, x2 are 0, right? So here x1, x2 are 0, then your gx is also 0. Okay? So we'll be passing through the origin. So the bias actually determining how far away you are from. We will see that more analysis later. So decision region is something like this, right? If your gx is larger than 0, right, that means g1x is larger than g2x, so you belong to 2. So the positive side of the line, it belongs to C1 space. Okay, the negative side of the line belongs to C2 space. Right. Once we determine from our data, let's say this data, we determine this W1, W2, W0. Right. Then having new data, when we predict, we just see, hey, where are the X1, X2? Right? If it's on this side, we say it's negative. Okay. Any questions? Right. Let's continue that. So let's take a little bit more intuition here, okay? So we have a geometric interpretation of what it means by GX, right? So here's what we do. Okay, so let me see. Let's come back again to this example, right? So we have X1, we have X2, and we have this line, okay? And we assume these 2 points are on the hyperplane, right? On this line in 2 dimensions. Right, so this is we have. Oh, so in this case we cannot call x1, x2, right? So this is a little bit confusing. Right? So basically this x1 is a vector. It means this point. Right? This x1, x2, these 2 coordinates together. So let's see how to handle this. Okay? So yeah, it's a conflict notation. Okay. So basically we say we have 2-dimensional case. So this is maybe the first dimension. Okay, let's say dimension 1, dimension 2. Okay, and then we have a function. Okay, and then we happen to have 2 points on it. X1 and X2. Right? And if that is the case, okay, then when it's on the line, if it's on the upper side of the line, it's positive. Negative sign is negative. Right? On the line is 0. Right? So if it's on the line, this means G1x equal to G2x equal to 0, which means, this is G1x, right? So this is G2x, okay? They are equal, right? If they are equal to 0, okay? If they are equal, you can shift this, right? So you move, so this W1 cancels, okay? And then you move X2 to 0, right? So it's X1 minus X2. So what does this mean? What does this mean? By the way, if you have 2 vectors minus together, it's this vector, okay? If you cannot see why, just using origin, right? So the first vector is this vector, okay? The second vector is this vector, x2, okay? And if you minus 2 vectors, it's really this vector, right? Because, you know, if you have this vector x1, oh, x2, actually, it's a reverse vector, okay? If you have x2, x1, no, it's this direction. Let me see. Yeah, it's a reverse direction, okay? It's this direction. Because if you have x2 here, right? And then add this vector, right? Let's say this vector, plus x2. Right? It's really x1, because these two cancel. It's this vector, right? So you know the vector follow this direction equal to this, okay? If you know the vector notation. So we will ignore those things. So basically, it says this is a vector along this line, okay? Right? And this w is another vector, right? So this vector times this vector is 0, which means this vector is basically perpendicular to this line, okay? It's a 90 degree, okay? Yeah, let's come back. Okay? Yeah, so here is the example, right? So this is w, right? It's 90 degree, it's perpendicular coming out of the plane, okay? So this is our w. So w is orthogonal to this vector x1 minus x2, but it's along the plane, right? So it's orthogonal to the whole hyperplane, okay? And we can express any point in this way. Because of this reason, we can express the point at something like this. Let's see how to describe it. Okay. So think about it, right? So you have two-dimensional space here. Okay. This is the origin, right? And now you define a xp, which is normal projection x onto the hyperplane. So firstly, you have a hyperplane. Okay? Then you have another point x. Okay. Then x, if you perpendicularly point to here, right, you have an xp that is on this plane. Okay. If you have a perpendicular point on this plane, right? So then here is what we mean. Okay. So x is equal to xp plus, so xp is this factor, okay? X is this factor. So plus this factor, okay? So what is this factor? This vector is exactly, along this direction. This direction is exactly this, okay? This is a unit vector because this is the w is perpendicular to this line, okay? But it may not be a unit vector, right? It may have some magnitude. You divide the magnitude, it's a unit vector along this line, right? And then you times r, okay? Then it's a less r vector. So this is exactly means the direction here is r, okay? So the distance from x to this hyperplane is r. Any questions? So this is just a definition, okay? If you already have a line, then we have an arbitrary point, any point here, we can always map into this foot on the plane, right? So it's p, and then we can represent like this, where r really means the distance from this point to this point. Okay, so this is what we are defining. We are defining those things. What is xp, what is r? Here we are just defining it. Okay, then we can write it like this. All right, let's think about how to compute r. Right, so we know that r is really the distance from a particular point x to your hyperplane, right? And this is important because if your x is on positive side, it's positive class. If it's on here, it's on the plane. Right? It can be positive or negative. It's on the other side, it's negative. Right? So the r is important. How far away you are from the boundary. Okay. So how to calculate r? Remember that our gi, right? Gx, g1 minus g2. The gx is of this shape. Okay. Additionally, we say that the x point, this x point, can be represented using this function, right? Okay. So then we have this, right? So let me see this. So so if basically we are saying this x is equal to xp plus r times the unit vector, okay, and this wt times 2, okay. And so when we put the x in the previous equation here, we will get this one, right? And next, so firstly, for now you should know this is what? This is your vector length squared, okay? I hope now you should know it. Right, so this is inner product of the vector itself. It's W1 square plus W2 square. So this cancels one with this, and it's R times W, which is this. So additionally, we have two terms. Okay. So what are these two terms? Right. This is WT XP plus WZ. Right. This is really GP, GXP. Okay. Why? If you look at this, right, if you put XP here, it's really GXP is to WT XP. Okay. So this is GXP. So finally, what we get is this. Okay. So GX is equal to GXP plus RW. Okay. Any questions? Yeah, let's clear a little bit. Okay, so we don't have so many hands. Okay. Right. So another important thing that you need to pay attention. What is GP? GP is exactly mapping on this line. Okay. So any point on this line, this thing is 0. Right? So we only have R W. Okay. So we can write things like this. Right? So what is R? Right. So what is the R? So this distance from the X to the point. R is really, if you look at these two terms. Okay. RW equal to GX. Yeah, R equal to GX. Right? And one thing you need to pay attention, this is vector length. Right? This is always larger equal to 0. Right? And that means the sign of R, whether it's positive or negative, really depends on G. Okay? Right? If your G is positive, which means it's belongs to C1, right? Then it's on this side. So this R is positive. That's it. This is maybe positive 5. Well, symmetrically, if your X is here, this will be negative 1. Okay. While if your R is in the middle, it will be 0. Okay. The magnitude is how far away perpendicular distance from X to the hyperplane. Okay. But the sign is belonging, saying which class you belong to. Any questions? So far, we only look at the W, so relation to R. But R is only relative to W. We also have a W0 term. Right? So W0 term, as I said, is relative to how far away it's from the origin. Okay, this. Let's take a look at it. So let's assume that the X is on the hyperplane. Right? So Gx is equal to 0. Right? So in this case, what we can do is we divide both sides by the magnitude of the size of the length of the vector. Right? The 0 divided by this is 3. Here we can write it. Then we can move this thing to the right hand side. It will be negative. Right? But we don't care. We don't care about the sign. Right? So we just take absolute value on both sides. Okay. Right? So this side we take absolute because these two inner product can be positive, it can be negative. Right? And in this side we just need to take absolute value of W0 because this is always non-negative. So what does this mean here? Right? So this is saying that the orientation of the hyperplane is determined by W, right? Because we know that. So this is what we are saying. Okay, so the first sentence is relevant. Okay, so the first one is what we talked about before, right? So if you have a hyperplane, so it's not always this is positive, this is negative, right? Sometimes this is positive, this is negative. Right? In this case, your W is along this direction. So in any case, the orientation of the hyperplane is determined by W. It's like a 180 degree flip from here all the way to here. That's it. Okay. But another concept is the distance from this hyperplane to the origin. So this distance. What is this distance? Right. So this distance is exactly this way. Okay. How can we see this? Right. So remember, X is the point on the hyperplane. Right? So this point, let's say this guy is X. That's it. Let me clear a little bit so that you can see clearly. I'll say this is the hyperplane, and then we give a virtual X. Okay? Oh no, not this. It's on the plane. Okay? We give a virtual X. Okay? And now what we do is this, right? So firstly, we have the X vector, but then we take an inner product, right? Inner product with this vector. And we know that this vector is along this direction. right? So this is unit vector on this dimension. Okay? So basically, in the product, this is what? This is x times this unit vector, okay? Unit vector u, which is 1, okay? Times cosine x u, right? So these two, that's it. So basically, it's along this direction. How many components along this direction? So this basically gives how far away this plane is. Okay, this is 90 degrees to the origin. Okay, the x can be arbitrary because after cosine, it's always this. Okay, take this component because this is the unit vector perpendicular to this, right? So this thing is of this side, right? So if your W0, then it forces you to be passing through the origin. Okay. Another thing is actually, how far away the magnitude also is impacted by the vector length of the W. Okay, the W is W1, W2, W3. It doesn't include W0. Okay, W0 is called a bias. So usually, if we call linear function, sometimes we can just call this as a linear function. Okay, if we have this W0 also with a bias, we call it alpha. But usually, we can call both just as a linear function. Okay, the alpha function also. Alpha is saying you emphasize the bias. Any questions? Yeah, for simply, W is determining the origin, right? So, and the distance is determined by W0 and W. Okay. So, yeah, let's go back to the previous one. A little bit more words here. Okay. So I'm sure that at least many of you know this thing. Right? So if you have a two-dimensional point xy, okay, this is xy. Okay, and this guy is what? This is ax plus by plus c equal to 0. This is line. Okay, and what's the distance from the point to here? Who can tell me?
ax1 plus by1 plus c.
Yeah, ax. Let's call this a particular value. x0, y0. Okay, yeah, x0 plus by0. Okay, divided by a
square root over a square plus b.
Yes, good. Okay. Yeah, that's exactly the same. I hope you can see. Okay. This is W1, W2. Right, so
Yeah.
And the gx0. Okay. So this is a generalization of your low dimensional case to Hyperplane. Right? How far away this point.
Professor,
Yeah.
I have a question. Can you go back to the previous slide?
Which slide? Which page?
Can you go back to your previous slide?
This slide?
Yeah.
Okay.
So I just wanted to reinforce what you have seen. The distance between the line to the x, what we wanted to calculate is r.
Can you repeat what you say?
Distance from the point, orthogonal distance from the point to the line is r.
Yeah, exactly. So the x perpendicular distance to this line, but the sign depends on whether you are on the positive side or negative side. Right? If you are very positive, it's maybe positive 5, positive 10. If you are very negative, it's negative 5, negative 10. Okay, right. But the distance is 5 or 10. Is this okay?
Okay, Professor.
Yeah. Let's continue. All right. So next, we consider multiple classes, right? So previously we talked about 2 classes. Multiple classes, then we cannot do G1 minus G2, right? So we have to list all those pairs of parameters. Okay? And if we have multiple classes, right, something like this, right? So each class Ci, okay, have a function associated with it, right? And but our logic is still the same. This is just a say whether you belong to class Ci or not. It's still a discriminant. Okay, it's still a binary classifier, right? So if you belong to class Ci, you're positive. Otherwise, you're negative. Okay. So this is saying that for each class CI, for each class, let's say this C1, these circles, okay? Right, so there exists a hyperplane H1, this H1, okay? So that along the positive side, you only have C1. Along the negative side, you don't have C1. You have all the others, right? So that's C1 is on the positive side, all the others lie on the negative side. Then this is, we call it linearly separable, okay? So in this case, in this example, they are linearly separable. You can see it, right? So for example, here, if you look at this class, you can use this one, okay? Well, if you consider, let's say this class, right? So you can use this one, okay? On this side is square, on the other side is not square, okay? And so you can see that it's not always holding, right? So it's very important that each class is belonging to, let's say this is belonging to this is belonging to this, okay? And this is belonging to this, right? And you cannot cross into this kind of boundary. Otherwise, this will not hold, okay? So this is pretty strict. Linear separable classes do not always happen, right? So we need to generalize this. Right, so what we are saying is this, right? So ideal case is just saying, hey, if I give this classifier, right? So if whether I belong to C2, right? So if I belong to C2, then what we have is G2 is a positive value, right? G1, G1, and G3 should be something negative, -10, -1, okay? Right, so obviously it's on both sides, right? So, and this may not hold, right? So maybe this is not -1, maybe this is positive, right? So then this does not hold. So in general, if that happens, okay, so we will have this this view, okay? Right, instead we require only one of GI is positive, the other should be not positive, right? We can say, hey, even if you, let's say G2 is 5, right? G3 is -10, G1 is -10, and another class 1, right? So we will take the maximum, right? So this may be class 2, this class 3, this class 4, right? So we will take this one, even though this is also positive, okay? We will take the maximum. And so this is actually quite often used in first program machine, where we usually have this kind of binary classifier as a unit classifier. Okay, then how do we extend it to multi-class classification? Usually we use what we will be talking about in these few slides. Okay, so it is possible for multiple or even no GI to be larger than 0, right? So let's say if your score for C1, C2, C3 is this, right? So let's say if you have -1, -10, -100, right? So of course you choose this one as a class. Right? It's the least negative, right? So it's very unlikely to be this class. This is not so unlikely, but yeah, it's still negative, but we will choose this. Okay, so we just take max. So geometrically, a linear classifier partitions a feature space into k-convex decision regions. Okay, so here's what we mean. Right? So if you look at here, if you look at this hyperplane, what is C2's decision region? It's really something. A convex region is relevant to the convex function. Okay, convex function is writing a line and it's a bow. Convex region is saying something like this: if you have any two internal points in the region, and you have a linear straight line between them, a segment between them, every point on the segment is also in the region. Right? So this is a convex street. Right? So this is not a convex street because if you have two lines, the line is some point outside this region. Okay, so here only when each decision region form a convex strip, then we satisfy this. Okay? Otherwise, we have to use a max. Any questions? Okay, now let's look at a little bit less strict case. Okay. So the previous method is good in terms that you just call the classifier k times, right? If you have k class, let's say if you have 10 classes, you just call 10 classifiers, right? So each has a GI, okay, 10 times. Right. Another case here, actually, it's more computationally expensive. Of course, if you do more, you want it to be more accurate. Right? So this is actually also used in supported live machine a lot. Okay? So if your classes are not linearly separate, right, this is possible. Right? So like this case, sometimes, if you look at look at this class, okay, you cannot put a line. If you put this line, some circle here, some square here. Ideally, you want to put a line to segment out, but it's actually on this side, right? So you have no way to put a line. If you put a line here, you will miss out some cross. Okay. So this is a case that is not linearly separate. Right. So we will turn into another case. Right. So we want a pairwise separate. Right. So what it means is, hey, I don't care about square. Right. I only care about C1 and C2 at this moment. Right. So H1, 2 will separate them perfectly. These two are linearly separate. Okay? And these two are linearly separate. And finally, these two are linearly separate. Okay? This is called a pairwise linear separate. This is actually easier to achieve. Okay? But it will be more expensive because if you have 10 classes, it will be 10 times 9. It's 45. Okay? It's instead of 10, the times the discriminant function call, you have to call it 45 times. Okay? This is more expensive. And this is a discriminant function here is a linear function, right? If you use a support managed machine, it's a classifier. It's more expensive. Okay, we will see support managed machine later. Here is just to give some concept. So it's easier for classes to be pairwise linear separate than linear separate, right? So here pairwise separate, but you have no way to separate one class from all the rest. So the discriminant function looks like this, right? So if for class pairwise, we only care about class I and class J. In that case, we find a linear function that class I is positive, class J is negative. For the others, it can be positive and negative, right? If your data item belongs to class 3, right? I don't care, right? I only care if your data is class 1, it can be on one side of the plan. It's class 2, it's the other side of the plan. And for class 3, class 4, in your data set, it can be anywhere, right? For this particular Gij, okay, G1, 2, right? But you will do this for every ij case. Now the decision rule in any test case, right? So the reason we want to say this is, again, even for a pair of data, it may not be linearly separate. If you think about the previous circle case, right? So the family car case, right? It's still not always holding. Okay. In that case, what we will do. But again, the previous case is not good, right? So it's we use the wrong function. Okay, we should use the generalized mnemonic. Okay, but anyway, even pairwise separation is not always guaranteed. Okay, another case is let me give you some. Right. So assume your data point is actually linearly separate. Okay. But unfortunately, because of measurement error, some crosses here, some circles here, some very small noise. Okay, then it becomes nonlinear separate. Right. So this small noise will cause a classifier shift a lot of the hyperplane. Okay. So that's why we later have a support vector machine using called epsilon insensitive loss function. Okay. We will see that later to handle this kind of small noise. And sometimes you will have an outlier, right? So this is mislabeled. It's very positive, but somebody just don't do the job. They would have meant. Right? But if this is not a lot, this kind of thing can also overcome this problem. But here we are just thinking about strict case, okay? Not so robust. And so if for any case, right, it may not be pairwise linear separable, then we will do this, okay? Right. So So we will, for example, if you have C, G, let's say 2 is the actual class, okay? G21, G23, okay, are all larger than 0. Right? That means G21, right? So 2 is preferred over 1. 2 is also preferred over 3. Of course, you take 2. Okay, so this is the decision. Right? But this is the ideal case, right? If you cannot find such a case, right? And for example, for G21, G23, it's all less than 0, right? But if you do this also not just for 2, you also for 1 and 3, you find that it's all also like, let's say there's no clear winner, right? So clear winner means you are winning all the others, right? Maybe you just win one of them but lose the other. Again, you don't satisfy this, okay? And if that happens, we will use a relaxed decision tree, okay, which is this one, right? So what does this say? This is saying, let's say you have you have class 1, 2, 3, let's say I and K. That's a K class. Okay. Now, so what we will do is, hey, how I win 1, we have a score, right? How I win 2, we have a score. How I win 3, we have a score. How I win K, I have a score. Right? I eliminate my own score. I don't consider. I consider the other K minus 1 classes. How I win them, right? The larger the better. I want to call it. Okay? A solution sum them up. So this is totally how I win the other class. Right? You also do this for the other class. Let's say 2, I consider 2, 1, 2, 3, 2, K, not include myself. Right? And for each class, like 2 and I, right? So we have a score. Right? Then we find the one that maximizes score. Right? So because we want to find the class that maximizes GI, G1, G2, G3. We want to find the maximum. Okay? So basically, this is we are doing if we don't have strict case, right? Any questions? Okay, if you have no questions, we will take a, let's say, take a 10 minutes break, and then we'll come back and talk about logistic regression, okay? But we do call it logistic discrimination for some reason. We will discuss later, okay? We will come back at 6:25, and we will take a 10 minutes. Okay, thank you. And if you have any questions, please feel free to ask.
Professor, I have a couple of questions.
Yeah.
Let's say we have a real life. I'm talking about real life problems. When we want to deal the machine learning through machine learning, we have, let's say we have given a 400 columns data.
Okay.
And what columns we need to choose in order to build the model, and moreover, what are the do I need to try all the models that are present for given data, yeah. Or how should I know based on the model, on what data, what model should I use? Is there anything like that?
Yeah, we will teach that in later lectures. So there are two kinds of ways. Okay? One kind of way is to do PCA, for example, to do the dimensionality reduction. Okay, this is called feature extraction because the original features may not be the best. It may contain some noise. Okay, so if you take the principal components, maybe the data quality is even improved. Okay, and you will have less dimensions. It's okay.
Okay.
Yeah.
Okay, but how would you feed for the training data? I mean test data then. How even you do the test data in the same manner?
So when you do PCA, it's a bunch of linear transformation, how from the old space to new space, right? From X to Z, right? And then these functions will be fixed. Okay, when you do the test, you just do the same transformation, and then throw the new Z into your test file. Okay.
Okay, and then coming to the what model should I use then after PCA, the data will be reduced. Then should I use all the models which are present, or and in what approach I need to go to use the models?
Okay, let me see this. Okay, so basically we have one way is dimensional reduction. Okay. So dimensional reduction means, so this is later. Okay, so if you want to mention now, I can do it. Dimensional reduction means we will transform something into a new space. Okay, originally you have maybe 100 dimensions. Okay, now you transform to 5 dimensions. Okay, but after transformation, it will be a linear transformation. Okay, so basically, let me see. So there's a one way called forward search and backward search. Okay, this method actually you keep the old features. Okay, let's say you have 100 features. I just wanted the most discrete 5 features. You can use forward and backward search. Okay, these are in scikit-learn, I believe. Okay, you can Google scikit-learn. Scikit-learn.
I understand that, Professor. Through this, I can select whether the variable is contributing to my model accuracy or not, such that we will be eliminating the variables.
Exactly. So you just include a feature selection package, and then you. So what we are teaching you is telling you all these things are there. Okay, in this lecture, and then you will know, hey, scikit-learn is so powerful, it must have this library, and then you search for it. Okay, so it will do something. So let me see. So this is a feature selection. Right? So select from model. So I think this is not it. Let me directly go to. So this method called RFE, okay, recursive feature elimination, right? So I think usually people will use this one, okay? Let me see what is the other example. RFE, okay? So you will do something like selector, and you will select some features, okay? And you say, hey, feature, I just want to stack 5, right? So then you will use the most discrete 5 features. Okay, these features selected will be the older attributes. Let's say you have 100 columns. You will select 5 of them. It's okay?
Okay, Professor.
Yeah. Another way is, this is called a feature selection. Right? So you select 5 among the 100. Okay. Another way is called feature extraction. Okay. Like a PC is one way of feature extraction. After feature extraction, basically do a linear transformation. Let me see whether I have a diagram to show this. Yeah, let's use this as an example, because this is called a factorial analysis. Okay, the older features are like xi. Now you have the new features there. They are linear combination. Okay, so your new feature is a linear combination of your old attributes. Okay, they are not your older attribute. We extract new features. Is okay?
Okay, Professor.
So then if you have this relationship, then you can extract the 5 best features, new features from your older 100 features. Okay, and then you can use these new features throw to your classifier. Okay, and because this relationship will be learned when you do the PCA for them, right?
Yes, Professor.
Yes, Professor. In the new data, you have the row, you throw the 100 to these weight matrices, you will get the 5 features. Okay, and then you throw to your classifier. It's okay?
Okay, Professor.
Yeah, again, so you can just Google scikit-learn PCA. Everything we learn here has a scikit-learn.
Yeah, I know about PCA, Professor, but my next question was, after performing PCA, I will get the reduced data. I agree with that. But what models should I use on the data? Should I use all the models which are present, right from statistics, machine learning to deep learning? Or based on what data I need to choose what model should be, okay, this is the threshold accuracy. I can't get more than this accuracy.
So this is problem dependent. Okay, so let me first close this, because this is not our slide. Let's go back to this. Let me pull out something I can write. Okay. Yeah, there's some space here. Okay. Yeah, the model here, actually, it's dependent. For example, if you only have, let's say, a popular model people use for drug tests, right? So if you have maybe 100 people or 10 people, right? And some are positive, some are negative, right? So you see whether the drug is effective, okay? Right? So you will use logistic regression, what we will be teaching here, okay? But logistic regression is a very simple model. It's a component of neural network, okay? And if you have many logistic regression, it becomes a neural network, right? And then neural network itself can have multiple layers and way more complicated, right? The reason you don't use neural network is because your data samples are too small, okay? And you have too many parameters in a deep learning model, right? So if you just have 10 or 100 or 20 samples, right? You don't want to use deep learning, okay? Right, you use simple models like logistic regression with some regularization because you want to overcome some overfitting, right? If you have lots of data or your data is very rich, right, you use deep learning, okay? Right, or if you have transfer learning, you can still use the complicated model, right? Because they are really good, already trained to really good positions in the parameter space, okay? You're already here, okay? So it's not far away to the best one. Otherwise, you may go to a suboptimal case, right? And you go to here, which performs pretty bad. Okay, that's a large area. Okay. Yeah, this is one thing. Another thing is that I think there's a, but usually what people do is just try a bunch of models. Okay, so scale. So there are some decision tree kind of rules that you can follow to decide how to do, right? So you start and you see how many data you have and which data, which problem you go to which model, okay? So they have this kind of second algorithm. You can also follow this rule. Usually it works pretty well. It's okay?
Okay, Professor.
If your data is too small, then you get more data, right? So if you at least have 50 samples, then you continue, or right, if you are putting a category, it go to classification, right? So you know, and then you see how many samples you have, you use different methods. Okay. Yeah,
okay.
But again, this is not always accurate. You just try all the method and see which one works well. Okay.
Okay.
So, okay, that's pretty much it. I think we should begin. Yeah, let's begin then. All right. So I'm not sure whether all students are still here. Just in case some students are not here, we'll describe logistic regression first, and then we continue. Okay. So what is logistic discrimination? It's the same as logistic regression, but logistic regression is used for classification. The name is a little bit confusing, right? It's called a logistic regression, but it's for classification, not for regression. Okay, it's for binary, 0 or 1, okay? Positive or negative, right? It's kind of like regression for the probability, right? So if it's larger than 50%, it's 1. If less than 50%, it's negative. Right? This is success probability. Right? So you can also treat it as a regression on the probability that you are positive. Okay, so it's a little bit confusing. Okay, but usually we will just use it as a classifier, right? And actually 50% can be changed. Right? You can try different 10%, right? If your confidence is low, right? So like let's say you require very positive, right? 80% probability to be positive. You think it's positive. Otherwise, you think it's negative, right? Very selective. Right? This is also okay. So when you change this threshold, you will get an AUC curve, as we said before. AUC curve, ROC curve, and AUC is the area and the curve. Okay, all these are actually generalization on like logistic regression or those kind of binary classification models. Okay. Okay, now let's take attendance. Yeah, again, so because we will share all those videos to YouTube, right? So we are using YouTube. I cannot find my mouse. I have to go back here. Yeah, and pull out my mouse. Let me clear this blue bar also. Yeah, I should not use this. Yeah, and because we have YouTube videos, you should utilize it. If you don't understand, you watch twice, 3 times, and you can control the time bar, right? So we don't have the progress on each topic marked there, but you can try, right? So listen to where you don't understand again, because we will move a little bit faster because previously we are a little bit slow. Why I cannot find my mouse again? Yeah, it's right. Okay, let me see. I think Christopher will not be here, so let me mark as leave. Gahada,
Yes, I'm here.
Thank you. Pratash?
I'm here.
Chun Yao? Chun Yao Chen?
Yeah, I'm here.
Okay. Somehow I cannot find my mouse again, so why? That's weird. Okay, let me continue. Chun Yao Chen, Ting Chen?
Yes, I'm here.
Okay, Deepak? Deepak, Dulao?
Yes, I'm here.
Okay,
Yes, I'm here.
got it. I
It's a
cannot-
problem.
Maybe I cannot play it. If I play it, I will not find it. Yeah, I think PPT and they have some conflict. Pat?
Yes, sir, I'm here.
Okay.
I'm here.
Okay, got it. Okay, Muhammad Harris?
I'm here.
Okay. Adil? Adil?
Yes, I'm here.
Okay. Kalal?
I'm here.
Okay. Boniface?
I'm here.
Okay. Let me run this just. Amulia?
I'm here.
Okay, let's go to the next page. Okay, I assume it's not meant to ask. Okay, so Latif? Latif? Okay. Mingyong Liu?
Yeah, I'm here.
Okay. I see a chat. Let me see. Oh, Latif is here. All right, so that's it. Let's come back because we need to finish this slide today. Maybe we cannot, but we will continue next time. Okay, so hopefully we can finish. So recall that if the class conditional density, right? So here what we will do first, we will use generative models. Then we will go to the discriminant model. Okay, so we will first revisit the parametric models using the density class densities. Okay, so remember that in the Gaussian, if we share a common covariance matrix, right, then the hyperplane, the separable plane between the two classes will become a hyperplane, right? It's a linear. Okay, this is what we see last time. So basically, this is a conclusion from the previous slide, right? So there's a quadratic term that is gone because it's a fixed, it's the same quadratic term for both classes, all the classes, right? It doesn't matter. Okay, so then we have this linear coefficient in our Gaussian model, high dimensional Gaussian model. Okay. And so given a data set, right? So what we will do, we will find the sample mean and the sample variance, right? And then plug them in here. Then we will get the linear plane that we want. Okay. So this is what we see last time. Now let's look at the two class example, right? So we assume that when you see data X, it belongs to class 1 was probably Y. Okay. And it belongs to class C2 was probably 1 minus Y. Okay. So here it's like a Bernoulli distribution, right? So it's like a P and 1 minus P, right? But there's some difference here. Okay. I think after taking attendance to students that I think I can track them actually because of the Zoom is with Canvas. Yeah, let's see. Okay. And so but it's still different. Okay. The difference is that it's conditional X, right? So if you look at the table, right? So you have X1, X2, blah, 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 we have some features, right? This is a class. Whether you belong to 1 or class 2, right? So whether you belong to class 1 or class 2, it depends on your features, okay? When you have those fixed features, right? So in that case, maybe you have 60% belong to class 1. While you have another set of features, you only have maybe 40% probability to belong to class 1, okay? So this is actually not a pure Bernoulli, right? So this is depending on these features, okay? So this is a problem setting that you need to clear. I think someone is not muted, so let me. Okay, I temporarily mute all. Okay, so if you want to ask questions, just let me know. All right, so the classification rule will be very simple, right? According to X, if you find that your probability belong to class 1 is larger than 50%, right? You will choose class 1. Otherwise, you will choose class 2 because the other class is more than 50%. And equivalently, we can write something like this, okay? Right, so if your Y divided by 1 minus Y is larger than 1, then you will choose class 1, right? The reason is very simple, right? So this thing equivalency Y is larger than 1 minus Y, right? So this is more likely, this is less likely, okay? So you will choose class 1. Equivalently, you can also take log of this, right? And take log of both sides, you will get this, right? So because, log with natural base is something like this. If you, this value is larger than 1 on this side, your Y value is positive, okay? Any questions? Yeah, let's introduce some terminology here, okay? So this ratio, right? So the probability of positive divided by the probability of negative is called odds, okay? Odds of 1, right? So X divided by 1 minus X is called odds of X, okay? If you further take log, it's called the log odds, okay? Or we call it the logic function, logit of X. Okay? Now let's look at the logic function of, let's say, of this thing. So basically, this is logic function, okay? And now, Y is what? Y is likelihood that you belong to class 1, okay? Now we put it here, it's really this thing divided by 1 minus this thing, okay? Of course, we have the log. And 1 minus C1 is C2, probably, because we are considering binary classification. And next, we know that this is posterior. Posterior equal to prior times the general probability, okay? This is the same, okay? And because these are product, right? These are this times this, okay? And taking log, taking out, we become summation. And this term is still here, right? We don't know what it is. It's just some prior constant, okay? This term, we know that it's what? We are going back to our Gaussian distribution, high-dimensional Gaussian distribution, right? So high-dimensional Gaussian distribution is represented like this, okay? There are some terms and exponentials and so forth, right? And here we need to call our pinout. Okay, so let's first do this, okay? So this actually, we will see that this is a linear function of X, okay? And W and W0 will be equal to this. So let's see why. Okay, firstly, this term, they cancel. Okay. Now what we have is this exponential divided by exponential. Right. So we say exponential A divided by exponential B is equal to what? Exponential A minus B. Okay. Right. And further we take log. Okay. If we further take log, this cancel with E, it's really A minus B. Okay. So this whole term is really A minus B. Okay. And let me clear this a little bit. All right, so the next question is what is A minus B? Right, so basically we say, so this constant we can take out. Okay, so this is 1 by 2. Then this term minus this term, right? So we have the first term is this term. Okay, this term is basically we say that X, this times this times this. Right? So this is this with inverse times X. Okay. That's this term and the minus me. So this is minus X. Okay. And then we have the other term. And last time we see that they are equivalent. Okay. Of course, we have the transpose. Okay. Mu transpose. Okay. Finally, you have another term. Because this is negative, negative, you have a plus. Okay. plus mu1 transpose sigma minus. Okay, so if you cannot see why the other term is the same, you just see this is a scalar. Okay, this is a quadratic form. Right? So it's scalar. It's transpose, and itself is equal. Okay, so this is the top, right? The bottom is something similar, but symmetric. Right? So we have the same term. That's why if you have these two terms minus, they're cancelled, right? But here you cannot cancel because this is mu1, right? This is mu1. The other is mu2. Okay, so we have basically the first term is -2, this thing minus the same thing but have mu2. So that's mu1 minus mu2 with C. Okay, and this x is this x, but the transpose, you know, we can write also this as transpose, but well, it's in the product between two vectors. So this xt is it's a current. Right? You can see there's no coefficient. This is because it's a -2, 1/2, and minus cancel. Okay, that's why W is this one. So we have another term. Another term is really, you know, we have this -2d. Okay, and then we have this minus mu2 transpose sigma minus mu2. Okay, so these two should minus the other, right? And then we plus this constant. Okay, but these two terms, let me clear this a little bit so that we can come back. Okay? So basically, we are saying that so this term is equivalent to what? We say we want a mu1 transpose sigma minus 1 mu1 minus mu2 sigma minus 1. This is transpose. Okay, so we want to show that these two are equivalent. Okay, so they are really equivalent, right? So for example, if you think about this is quadratic form, right? So this is mu1 is, let's say, a squared, mu2 is b squared. Okay, and we know that this is basically a plus b times a minus b. Okay? It's just a generalization of that with covariance matrix in the middle and the high dimension, right? But how do you see that, right? So you can time out these two terms. You can see they cancel. For example, this times this times this is this term, okay? And this times this times this is this term, minus mu2, mu2, okay? And there's the other term, right? Mu1 times this times minus mu2. Right? So this is mu1 sigma minus, okay? And there's another term. I think there's a transpose mistake. Okay? And there's another term called mu2, right? mu2 transpose, okay? Sigma minus 1 mu1, okay? So mu2, mu1, this is positive, right? But mu1, mu2, this is negative because we have a negative. And these two are actually the same thing, right? So if you take the transpose, they are the same thing, okay? If you take the transpose, because this is scalar, transpose itself, this becomes mu1 transpose, sigma, because this is the metric, okay? This is covariance matrix, transpose itself. And this thing transpose itself. So these two terms are the same, minus and plus cancel. Right? So these two are really, it's just a generalization of this simple factorization. Okay. But you may ask, why would we bother to make it so complicated here, right? So we can do this thing again. Right? This is for computational purpose, right? So you know this thing is a 1 row times a square times a column, right? So this is pretty expensive, right? So you basically have so many elements summed together. Right, so this is do this once. This is do this twice. Okay. Right, so we would prefer to do this once. Vector minus is and vector plus is much faster. Okay. This matrix is much slower. Right. Any questions? Okay. If this is okay, let's continue. So, yeah. Any questions? So here, what we have is this, right? So if we assume our model generally probably Gaussian, right? Then what we do is we from our data we gather the sample mean and sample covariance matrix, right? And then we, for example, class 1's rows we can get a sample mean, right? Class 2's rows we can get mu2, okay? And from all the rows, because we assume a shared covariance matrix, we can get. Then we get W and W0, and then we get this one, okay? So this is if we use a generic view. models. Right? And next we can do the sigmoid function. Okay, sigmoid also called the logistic function. Right? Logistic function is the inverse of the logic function we talked about before. Right? Logic function, if you remember, is log y divided by 1 minus 1. Okay, logistic function, the inverse function. So inverse function is saying that if you have x equal to fy, y equal to fx, right? Then the inverse function is x equal to f inverse y. That's it. So something like this. Okay, so y equal to fx. Right. So then x is equal to f inverse y. Okay. So there's a relationship like this. Right. So now let's derive the sigmoid function, and we will see why this is the case. Right. So sigmoid function has this shape. Right. So sigmoid function of a value. So here we are writing it out a little bit more complicated. The actual sigmoid function is very simple. Okay, sigmoid of a, let's treat the same thing as a, right, is equal to 1 divided by 1 plus exponential of minus a. Okay, this is the sigmoid function, right? We are adding some additional stuff here. Okay, so don't be confused. Let me see. Probably we skipped a derivation. Okay, we need to go back to this page. But here you remember sigmoid function is of this thing, right? And we want to show that if we put our linear score for the binary case, right? The linear score here, the sigmoid of the linear score is exactly equal to the probability that you belong to class 1. Okay. So in other words, if you have a linear classifier, get a linear score that the range is negative infinity to positive infinity, you can take a sigmoid function and you can translate it into a probability value that is between 0 and 1. Okay. So this is the high level stuff. Okay. Now let's do some simple derivation. So firstly, remember that the logit function is this function, okay? So basically, we know that this is what we talked about before. The logit of this probability is equal to this, right? And we derive this. I think this we derived. Let me see. I think there should be some other derivation. Oh, no. So here's what we want to see, right? So we just derived that, but we haven't explained why this holds. Why the linear score, if you throw it into a sigmoid function, it will return you the probability, right? This can be seen from the previous derivation. Let's go back to the previous page. So this is what we derived before, right? So let's repeat our conclusion, okay? The logit of P1, right? So it's equal to what? It's equal to a linear function, right? The linear score, your GI, right? Your GI is a linear function, right? It's a linear score return for your class I. In binary classification, it's a G1 minus G2, right? And with this score, it's equal to this thing. Or we can say it's equal to this thing, right? So let's write this as y, simply. Okay, so we are saying that log y, 1 minus y is equal to what? Is equal to this linear score, right? We write it as a, okay, this is a, okay? So this, if we take out this log, is exponential, right? And if we time this 1 minus y there, this is y is equal to 1 times y times this. So it's EA minus EA plus 1. Okay. Then we can move this thing to the left again. So this is y 1 plus EA. Okay. Equal to right. And finally, what we want is y, because y is a probability. Right? So y is equal to it's equal to EA divided by 1 minus EA, or 1 plus EA. And the next is we divide both top and bottom by EA. So this minus EA, this thing also divided by EA. So this will give you something like y equal to 1. This thing divided by EA is 1. Okay, this is 1 divided by EA. So 1 divided by EA is E minus A. Okay, so this is really the case, right? So this A is a linear score, and after taking the sigmoid function, you get y. Y is really the probability. Okay. So this is what you want to see, right? So if you put your linear score here and plug into a sigmoid function, which is the inverse of the logic function, right? You will get a probability that you likely don't be the positive. Okay, so this actually directly computes a posterior class probability, right? So this is posterior. Right? If you see X, how likely are you going to see? Okay, you don't even go to the Gaussian, those kind of things. So this is what we call the discriminative functions. Okay. And so yeah, so if you want to go back to the previous case, then you just do training. You from the data you estimate mu1, mu2, and sigma, right? And after that you will get w and w0, right? And then you throw to this function, okay? Then you will get a score, right? If you get x, you throw to this function because w0 already computed from the data, okay? And then you can get this function for a particular x. You will get the probability you belong to positive class, right? If it's larger than 0, you choose sigma. If it's smaller than 0, you choose theta, right? So this is equivalent to saying that if your sigmoid function of your linear score is larger than 50%, okay, then you choose class 1. Otherwise, you choose class 2, right? So how to see this, right? So let's assume that this linear score is 0, right? So this, you are exactly on the boundary, right? This is 0. So this thing is 0, right? Exponential of 0 is 1. So this is 1 by 1 plus 1. Okay, this is 50%, right? So basically, if you are positive, if it's very, the score is very positive, this thing has a negative sign, right? This goes to very negative. Exponential of very negative value goes infinitely close to 0. So you go closer and closer to 100%. Okay, you're very likely to belong to class 1 if your score is very high. Okay. On the other hand, if your score is a negative infinity, right, very low value, this after negation is a positive value. Exponential of positive value is very big. Okay, so this is 1 divided by a very big number. So your probability goes very close to 0. Right? Any questions? Okay, then let's continue. Right. So here's what we are talking about. This is the sigmoid function. So in this sigmoid function, we know that if this is your linear function score, right? This is the score. Okay, this is the probability of C1. Okay, right. So if your score is exactly 0, then you are 50%. Okay, if your score is very big, very positive linear score, right, then you are very close to 100%. If your score is very negative, on the other side of it, right, so your probability belong to the positive class is close to 0. Okay. So this is actually a special case of a class of methods called logistic regression. Okay, they are the same thing. Okay, logistic regression is logistic regression. Okay, because we use we are estimating P1. P1 is kind of like regression, right? But the P1 is actually used for classification. Right? So logistic regression is is a binary classifier. Okay. So here, this class of problem, actually, the key feature is this. We do not, the kind of method does not model the class conditional probability, right? The Gaussian probability. How likely you belong to class I, you generate this, right? But we model the ratio, okay? We model this ratio. Okay? How likely you belong to the positive class compared with the other class you don't want, right? You take the log, it should be linear. Keep that in mind. Okay? This is the key relationship. Let me highlight this. This is the class you want. Divide by the class you don't want. Take log. It should be the linear score. Okay. So this is we are doing the ratio directly. So unlike the prometric classification approach. Okay. Oh, by the way, so maybe you will ask. So we are talking about this ratio, right? So we are talking about XCI, right? C1 divided by XC2, right? But it's the same as this ratio. The reason is very simple. If you come back to here, this term is constant. Okay, so their ratio, this ratio and this ratio, it's almost the same. Okay, this is the prior, which is constant. Unlike the prometric classification approach, right? where we will estimate the generic probability. Right? Discrimination actually estimates the parameters directly, okay, from all the classes. Okay. Next, we will see the previous one. Actually, we are still using the generative method to derive it. Okay, but what we want to do is really tell you this. Right? So if you have a linear score, plug in sigmoid, right? So it will give you some probability. Right? If we ever have this probability concept here, okay, if we ever have this probability concept here, we are still considering, generic probability. Okay, right? Because we are considering this. Right? So logistic regression is not considering probability. Okay, we just bypass the probability step. Okay, let's see how we can derive logistic regression in this case. Right. Again, we have the training set. Right, we have the other attributes and the target attribute we want to predict. Okay, which is the classification problem. Okay, and we are considering binary classification. This is our data, and we know that it's a binary classification problem. Right, if it's 1, it belongs to the positive class. 0 belongs to the negative class. Okay. And we assume that once we fix the feature value x, okay, this is very important. If we don't fix the feature value x, this R will change, right? If we have a particular attribute, right, it's all this person, for example, right, this row, then R is fixed, okay? If the two people have the same features, then their probability that belong to class 1 is fixed, okay? So then R becomes a Bernoulli distribution with parameter y, right? Y is dependent on the feature. Okay, y is the probability that you belong to the positive class. So if we do something like this, right? So we assume once you condition x, right? This x is fixed, right? The probability that you belong to the positive class, right? So is following a Bernoulli distribution, where the probability is y. Okay. Here you need to pay attention. What is y? Y is PC1. Okay. So y is this, right? So y itself is a function of w and w0. Okay, the linear score functions, right? So we are directly learn these linear score functions. Okay? So y is a function of w. Okay? Keep that in mind. Okay, it's just for notation simplicity. We don't want to write the whole thing. Okay, so now what is the likelihood, right? So for one particular L sample, we know that the Bernoulli distribution can be written like this. But this is a successful probability. If it is 1, then you have y. If you have 0, then it's 1 minus y. Okay, this is for one data, right? And we assume that different data are ID distributed. So we take the product, right? And this is likelihood. If we want to compute the log likelihood, we need to take the log. Then this becomes summation, and this comes down over the log. Right? This is R log y. Okay, this is 1 minus R log 1 minus y. So this basically gives us something like this, right? So this is saying that we maximize the likelihood of it, right? It's equivalent to minimize the negative log likelihood. Okay, this is negative log likelihood. And in this particular case, the negative log likelihood is called the cross entropy loss, cross entropy error. Okay. So why we do things like this, right? So this is because I think everyone knows what is entropy. So if it's a binary class, let's say you have a P and you have a Q, another value Q equal to minus P, right? So the entropy is equal to what? It's equal to log P log P minus Q log Q, right? This is entropy. Right? But here the P, this P, and this P, this Q, the Q are of the same distribution. So if you have different distribution, right? So before log, you have one distribution, after log, you have another distribution. This is called the cross entropy, right? You have two different distributions, okay? This measures the difference between two distributions, okay? The distance between two distributions. So usually we will use this as the loss function. And if you know softmax, deep learning, they all use cross entropy loss. It's just that it's not binary, right? It's a P1, P2, P3, okay? So, and additionally, you need to pay attention. What is this? This is the probability P1, okay? PC1, okay? And it's equal to a softmax of the linear score, right? So this is between 0 and 1, okay? And this thing is what? This thing is a class, right? It's 0 or 1, okay? So this is either 0 or 1. It cannot be 0.5 or 0.9, okay? So this thing, we can call it a one-hot encoding, right? So maybe we can expand this slightly a little bit. Okay, so let's see whether we can. I think I need to stop playing this, otherwise I cannot find my mouse. Sorry. Do we have that? Yeah, here is example. Okay, we have cross entropy loss. Right. So here is a 3-class classification problem. Right. So let's say you belong to class 1, then the other should be 0. Right. This is R is 1, 1 minus R is 0. Okay. But we have 3 classes. But actually, when you have the linear score, right, the first the class 1's G1 is 0.7, G2 is 0.2, G3 is 0.1. Right. Then you want to compute what? You want to compute their cross entropy. Right. So that this goes with this column. This goes with this column. But this on top is a, is a binary value, okay? Only one of them is 1, the other is 0. In particular, this summation actually means there's only one term that is log the correct class. Does that make sense? Okay, it's a negative log of 0.7. The other classes, it doesn't matter, okay? So this is called the sparse cross entropy. If we go to, yeah, so this is a loss called a sparse categorical cross entropy, right? Because you only care about, for example, this is your class, you only care about negative log of this value, this score, okay? The other is times 0, it doesn't matter, okay? And there's also other cases, right? So for example, your labels are obtained by crowdsourcing, okay? Maybe you say, hey, whether this question is correct, right? So maybe 8 people say, hey, this is correct. 20 people say this is not correct. And then the true class is 0.3, 0.8, and the negative class is 0.2, right? So this label itself has uncertainty, right? So then in that case, you cannot use sparse categorical entropy, right? So you have to use not sparse, okay, just cross entropy. Okay? So again, TensorFlow is not what we cover, but just to give you some concepts. So later when you come back, you will know they're different, right? So you can see that the input will be different, right? One is actually a sparse one, just to give a, now here we will give basically 2 vectors, okay? We'll give 2 vectors. Okay. Sparse is just to give the index, that's a 0, right? This is 0th position, okay? So that's the difference. The input of the functions are also different, okay? And yeah, so that's pretty much it. Let me play. Yeah, just pay attention. Actually, only one term. Right. Between these 2 terms, only one term is 1. The other is 0. Okay? Only one log is active. So for this function, actually, we can show that no closed form formula exists. Okay. You may want to.
The other dress though.
What?
I know, but that's why I'm wearing it for dinner with you.
Oh yeah.
All right, Kanan, can you mute yourself?
Damn.
Kanan Strong?
What site is that? You know all the little sites.
What's happening there?
I know.
I think he probably muted.
It's the same site as the first one. So if you ever want to get me a dress, go to that site. Don't do no
Let
no
me
don't do that.
Let me handle this.
Or no Shein, don't do that. Do that site.
What that boy talking about? That boy about to get kicked.
Professor?
Yeah. Yeah, I just muted it all. Okay.
Okay.
Yeah.
Yeah.
I was finding the button. I'm not familiar with that. Yeah. Okay, so let me see. Okay, let's continue. I think it delays for maybe 5 minutes, right? So yeah, I'm finding this button. All right, so let's continue. Yeah, so one way to do this, right? So one way to do this is apparently, you have W1, W2, W3. You also have W0, right? You will do something like this, right? So you will take a partial derivative. So one way of this, because these W's are hidden in Y, okay? So we'll do partial E to partial Wi and set all these to 0, right? But unfortunately, you cannot solve it, okay? The solution doesn't exist. That's why we need a gradient descent, right? So there's a global optimal there, okay? And the reason there's a global optimal is because it's convex, okay? This function is convex, and you will prove this in your assignment, okay? Hopefully you can prove it. If not, you can, maybe I will give some hints in the next week until next Monday. If you still cannot solve it, we will get some hint, okay? You will prove this is convex. You need to go to the Hessian matrix to prove this function. Logistic regression itself, this loss function is convex, okay? But beyond that, if you have multiple logistic regression becoming a dense layer, fully connected neural network, it's no longer convex, okay? Let alone all the other neural technologies. But this special case is really convex, okay? We can show this. And you will do that in the assignment. Right, so this is the assignment, question number 4. And the next programming assignment will ask you to do the Newton's method, because Newton's method is mainly used for convex functions, okay? You will do a Newton method for logistic regression, okay? Yeah, let me add a few sentences here, okay? Let me do this. I think I will lose mouse. I have to stop. I'm sure. So let's look at second. Okay. Because logistic regression is convex, okay? So you can use Newton method to do it, okay? So there's a parameter solver, right? So you can just say, hey, Newton method, and then you solve the next assignment, right? This is not allowed, okay? You need to implement Newton method, okay? So you will use the conclusion of assignment 4 that we obtain, question 4 in the next assignment, okay? The written assignment. And then using that formula you derived to address, to write your own logistic regression function. Okay, you cannot just cosine-learn and do this, right? Okay, so pay attention to that. Otherwise, we will deduct mark significantly, or we will ask you to redo, right? Depending on the time. Well, if it's too late, then probably we'll just deduct a large margin scores, because you are not doing what we requested. Okay, so don't do that. Okay, but again, the reason it has Newton method is because the logistic regression itself is really complex, okay? And we will derive that. And by default, it will just use the other method, which is more linear. Right? So there's also quasi-Newton. Basically, Hessian matrix is n by n, right? So while gradient is just n. So n by n for very high dimensional, a lot of parameters, it's unacceptable, right? If you have 1 billion parameters, the Hessian matrix is 1 billion by 1 billion. Okay, so that's great. So that's why deep learning these days are all using, Adam, just kind of gradient descent kind of method. Okay, but the Newton method is very effective if, let's say, you only have these parameters, and it will run much less iterations. It will converge way faster. Okay, we will see that. Okay, any questions before I move on? Yeah, so previously we say we can take a derivative W and W set to 0 directly, right? If we can compute it, that's cool, right? So basically we have the optimal parameter, right? So we have W0, maybe a linear function, let's say. W1, and their derivative 0, these W0, W1 values will be what we want, okay? So minimize this, but we cannot compute it, okay? Then we have to do gradient descent, right? So we're here, we say, hey, this slope down, and this gradient is a bit large, we take a big step. And this is no longer so steep, I take a small step. Gradually you will reach here, okay? So this is called a gradient descent, right? Even though you cannot compute exactly, analytically, you can compute it numerically, right? Gradually go closer to this lowest value, okay? Okay, so this is the sigmoid function we see before, right? And so we can prove that if you take a sigmoid function, right, which is of this shape, right? If you take a derivative over the a here, okay? So this will be used in the next step. We will need to take derivative to do the gradient descent, okay? And firstly, we have this property, okay? You can show this is really holding, right? So let's prove this first, okay? And then we give you a description of why we have this. So let me take a look. So basically we say y is equal to what? Y equal to 1 divided by 1 plus e minus a, okay? So if we write, let's say we use chain rule, we write u as e plus e minus a, okay? So this basically is 1 minus u, right? So you know that if you take a partial derivative, it's what? It's u squared, okay? It's to the power of -1 becomes to the power of -2, but -1 should, right? But this times chain rule, right? Then you this u should take a derivative to a, okay? Take derivative to a, right? So 1 take derivative to a is 1, 0, okay? E, then you consider this as u prime, okay? Right, so e x take derivative x is ex itself. So you still have this thing, okay? U prime, which is finally you have u prime take derivative a, which is -1, okay? So this gives you what? This u is basically this thing. Right? So this is 1 plus e minus a squared times e minus squared. And this negate cancels. So we have this, okay? I think it's a little bit difficult to see. Just to keep in mind, this is positive. This is 1 plus e minus a squared. This is e, this thing. Okay? That's clear a little bit. So what we just derived, we just see that y dy by dA, okay, is equal to what? Is equal to 1 plus e minus a squared. This thing squared, okay, times e minus a, right? So this thing can be further written out into 2 parts, right? So you can write it as 1 plus 1 plus e minus a, okay, times e minus a. Okay. So you know these two, if you sum them up, it's equal to 1. Right? So this is 1, so this is the total. Okay. So this is basically saying, hey, this y is this thing. Okay. So we say this thing is what? This thing is y. This thing is 1 minus 1. Okay. So that's why we have this. It's okay. So the question is, why we want to write this as a function of y instead of a, right? So we can just use this, right? So why we bother? We don't stop here. We really go to here, right? So the reason is very simple. Okay, so exponential is very expensive in computer. Okay, right? So you know the ALU is algorithm logic unit, right? So this exponential has to use a Fourier transformation, etc. to close the gap. Okay. So this is much faster to compute, right? This is way slower. Square, so square is okay. If it's a square plus 3, this is square. It's like a multiplication. Okay. So yeah, so this is way faster, right? So instead of using the x value, you're directly using the y value to compute the gradient. Okay. This is actually how people implement this in, let's say, TensorFlow to do backpropagation, etc. Okay. Now, if you think of this conclusion is okay, right? Now let's what we actually want is not take derivative a, but a, as you remember, a is the linear score, right? W times x plus w0, right? So we want to update take derivative of e to what? E to w, okay, not to a, right? So this is what we want. Okay. So gradient is something, you know, along the negative gradient direction, right? Because we want to go down. Okay, gradient is going up, the fastest direction up. Okay, we want a negative direction, and this is step length. Okay, how far away you are. The step length is times the steep, right? So if you are very steep, you take a big step. If you are not so steep, you take a small step. But this is called the step length, also called the learning rate. So learning rate, if there's the step length is too small, what will happen is you go a long time, you still don't reach it. Okay, if your step length is too big, what you will do is you zigzag and you are still not able to reach it. Okay, so learning rate itself is a hyperparameter in BQ. Okay, usually we will start from 0.001. Okay, then we can try different numbers. Let me see. So this is empirical value. Okay, that's really how people do. Okay, so now let's look at take derivative. Okay, how do we do this? This we will go back to the function here. Okay, now we take a derivative w, right? W is hidden inside y. So according to chain rule, we should first take derivative y and then y to w. Okay, so if we take derivative y, log y, take derivative y is divided by y, 1 by y. Okay, so this r divided by y, this is what? This is 1 minus r divided by 1 minus y. But then we have the chain rule, 1 minus y, again take a derivative y, which is a negative. So this sign will become negative. Okay, so that's why we have something like this. Okay, negative sign, r by y. Then this is the chain rule. Okay, y should continue to divide by. Okay, and so keep in mind this term is the same, right? You can take it out. Okay, and then you can factor out into chain rule. Y is further a function of a, right? Y to a. A is a function of w. Right? A is a linear scale. Okay. And then what kicks in is this term. Okay. We can take this thing. Right? This is YL minus 1 minus y. Okay. And then we have this term. Okay. So we will derive this thing. Right, so we'll get this. Right, so the difference here is that we just write it out. Okay, so this is this is the previous term. Okay, y to a is this term. Okay, y to a. Next, a to w. Right, w. Okay, so how do we get this? So this is summation. Right, the one term, only one term is run to w. Okay, this wj xj and something else. Okay? If you take the derivative wj, you get the coefficient xj. Okay. So basically, this is one term before, this is the second term before. Okay. So this is one term, the second term. All right. So next, we can actually simplify the log. Let's see why. Okay. So this is very nice. Okay. So if you look at these two terms, right, and this times this gives you what? Because this y cancels, right? So this is RL minus RL YL. Okay. Then you have this term times this two terms, right? And this times these two cancels, right? This is minus 1 minus R times, right? So this is a minus YL. And because this negative is this negative, so this is plus RL YL. Okay. The next thing is the RL YL RL YL cancels, right? So this is really RL minus YL. Okay. So this looking super complicated, but actually it's very simple, right? And then this X is copied here. I hope if you guys cannot follow, you need to watch the video, okay? And so, yeah, because for assignment, we will have some derivatives, right? So for assignment 1, it's all about taking derivatives. And yeah, so this is one term, okay? About W0. W0 is exactly like before, right? So this thing is the same. The only difference is the last term. Last term, if this is W0, there's no coefficient, the coefficient of 1. So there's just times 1, okay? So this is essentially the sum, okay? So just this A to W0 is 1, okay? So the other is following the same model. So if you look at some intuition here, let's get some intuition, right? So because we have gone so complicated, right? So what does this mean? Now you look at this, what is this? This is basically your data table, right? So your data table. This is your else row, okay? And the J is, say, this J's column, J's attribute, okay? Right. And so here is what we mean, okay? So if your real value and your predicted probability, right? This is probability belong to P1. This is whether you belong to P1 or not, right? If this is correct, right? So this is the difference from the, let's say this is 100%, let's say you belong to positive class. This is not quite there. This is 80% we think it's positive, right? So there's still 20% gap, right? So we will boost this attribute node. We will boost this weight, right? This is because this is the WJ next time update, right? Okay, plus this. We'll boost a little bit, okay? Right, so basically we will boost according to the actual value here, right? So this is the intuition. So you can see one important thing is that different attribute features are independent. Right? So they all depend on this value, right? And then this weight is just the attribute values here. Okay. So this is intuition. And in reality, how do we implement it, right? So initially we have D+1 weights, right? So we will randomly initialize them. Okay, this is random can be uniform. Usually we use Gaussian, right? Standard deviation is 0.01 and mean is 0. Okay, that's deep reason why we need to center the data into 0. Okay, otherwise you may go a long way to get some optimal value, right? The center is unbiased, right? So you never know whether it's in which side, right? So then you just put in the origin, okay? And but you need some randomness, right? Because so usually we'll add some randomness. In this example, it's fine. Okay, in this example, because it's a convex, right? So this is what I mean. Let's say you have a ball and you have a ball and wherever you put, right? So wherever you put, it will reach the minimum because it's a convex. You can put a very large value here. It goes a long way to minimum. Okay, but for deep learning, okay, this is very important. For deep learning, you want it to be centered around 0 because it's non-convex. Okay, it's even more complicated, right? So this is if your layer is not too deep. If your layer is very deep, you use the Chi-mean initialization for ReLU or use Xavier initialization for sigmoid, okay, activation. Okay, so yeah. Now next is actually we want to repeat gradient descent to converge, right? Remember each parameter independently update, okay? This is a vector, right? And this is really depending on how far your real label for the T's data is regarding the Y. Y is computer using sigmoid. Right? Sigmoid O is the sum of the square. Okay, so it's a weighted linear combination, right? And then you update it accordingly. All right, so I think maybe let's see how many pages we have. Okay. I think we are very close, but we cannot finish it today. Let's maybe go to 1 or 2 more slides and we stop. So, but I think these are actually correlated. If we, yeah, I think I will just stop early and continue next time because when it's larger than K classes, we have to repeat it anyway next time. Okay, so that's all for today. And again, there's a lot of derivations. The important thing is first get the intuition, right? So I always give intuition, go to some website and give some intuition, okay? And then go to the mathematical details, right? and watch the YouTube videos. Okay, rewatch it if you are not familiar with that. Okay, and fortunately, nowadays in deep learning, these things are automatically handled. These derivatives are automatically handled. Okay, and so you don't worry about them. But it's good to, when we are learning fundamental machine learning, you need to know them. Okay, and some operations like trace, matrix factorization, etc., is not handled by deep learning often. Okay, not handled by TensorFlow often. You still need to know this. Okay, that's end for today. And I will be here for maybe 2 more minutes. If you have any questions, just let me know. Okay, thank you.
Thank you, sir.
You're welcome. Yeah, if you have questions, it's time to ask. Okay, otherwise you have to make an appointment with me or go to the TA's office. Again, because of the pandemic, I understand things are making the course a lot difficult to learn, especially if you want to form final project groups, right? So do go to the office hours, even if you have no questions, right? You can chat with the other student to identify your teammates, okay? From today on, we will have TA office hours, always have breakout rooms, okay? And so that you can start forming teams. Thank you. Okay, so it seems that no one has questions. Then we will see you next week. Okay. Yeah, have a good night.